I'm Desmond, and I'm a chemistry major here at Boston College. This summer I worked in the Birch lab to test and improve graphene biosensors by implementing microfluidics that seek to increase the sensitivity and selectivity of the devices. So in this talk, I'm going to give you a brief overview of biosensing and how the implementation of 2D materials could revolutionize this technology. Next, I'll talk about graphene and why it's unique and why we use it in our biosensing technology. Finally, I'll discuss microfluidics and how we plan to use them to greatly improve our graphene biosensors. So simply put, a biosensor is any device that can quickly and effectively detect the presence of different biological compounds. So the potential applications for biosensors are diverse and span many different fields, from biomedical to environmental. At the Birch lab, we're developing biosensors as a point-of-care tool for identifying bacteria and diagnosing patients with accuracy and efficiency. So it currently takes doctors days to send DNA samples to a lab and receive information on what sort of bacterial infection a patient has. With our graphene biosensors, it could take as little as 30 minutes. This diagram on the right gives a brief overview of how biosensing works. You start off with a substrate, in our case graphene, and a linker is first attached. So this linker uses P-base, and it attaches to the graphene using non-covalent pi-to-pi bonding. Next, a single strand of probe DNA is attached to the end of this linker. And finally, a target strand of DNA is introduced into the system. And if the two strands are complementary, they will bind. And this will send us some sort of signal to the person using the biosensor that alerts them to the fact that the DNA has in fact bound. So there's a couple important factors we want in our biosensors. The first is sensitivity. We want to be able to detect even minuscule amounts of biological compound in a sample. The next is selectivity. This means we just want our target DNA, or our probe DNA, to attach to only one target DNA. We want to be able to eliminate false diagnoses or false positives, so that we can begin treatment as quickly as possible. The next is speed. This is pretty obvious because the faster we can diagnose a patient, the quicker we'll be able to treat them, and this could save lives. So the final factor is size. Nanomaterials have allowed scientists to create what they call lab-on-a-chip devices, biosensors, which fit the entire biosensing device on chips, sometimes as small as a centimeter by a centimeter, which is the case in our lab. So this would allow every hospital to have their own biosensors, so they can run these tests on site instead of having to send it away to a lab, which takes a lot of time. Nanomaterials have basically redefined what is possible when it comes to all these different factors. And one of the most important nanomaterials is graphene. So graphene was first discovered or first isolated in 2004. And ever since then, it has been an area of intense research in the scientific community. Its 2D structure, it has a 2D structure solely made up of carbon atoms, arranged in a honeycomb pattern. And this gives it some pretty incredible properties. Among these are it makes it incredibly strong. So it's actually 200 times stronger than steel and a lot lighter as well. But the property we care most about for our biosensors is its amazing conductivity. So graphene's conductivity is a result of its unique band structure, and in order to understand why we use it as a biosensor, you first need to understand how band structure works. So band structure can basically be thought of as a plot of all the energy levels that an electron within a solid can occupy. For most materials, there are two bands, a valence band with lower energy and a conduction band with higher energy. The area in between these two bands is called the band gap, and it's basically all the energy levels at which there's zero probability to find an electron, basically all the energy levels that an electron can't occupy. So in order for electrons to move from one band to the other, they have to cross this band gap. They have to have enough energy to get across it. So materials can actually only conduct electricity when they have electrons in excited states. So the easier it is to get an electron to an excited state, to a higher energy state, the better the material will conduct electricity. So semiconductors are called semiconductors because their band gaps are relatively small. This means that they have, it takes very little energy, or it takes relatively small energy to excite the electrons and make the material conductive. Insulators, which conduct very little electricity, have larger band gaps. And then there's graphene. Graphene's band structure is unique in that it has no real band gap, only a single energy level that electrons cannot occupy. And we call this, this is called the Dirac point. So at this Dirac point, the conductivity is at its minimum, because conductivity is directly proportional to the density of states. You can think this is the more states available, the less energy it will take to excite an electron to the next state, and the higher the conductivity will be. The minimum conductivity results in a maximum, so this minimum conductivity at the Dirac point results in a maximum resistance, because as you can see here, the two are inversely related. So for our device, it is more convenient to create a plot of resistance versus energy, because this graph will give us a nice clear peak at the Dirac point. So for clean undoped graphene, this Dirac point will be at zero energy, because at this point there's no available states for electrons to occupy. So when we add the biomolecules to the graphene, however, they actually transfer their own individual charge to the surface. And what this does to the band structure is it fills up some of the states, as you can see here. And the graph of the resistance versus energy also reflects that. You can see how the peak of that graph is actually shifted. So using what's called a gate voltage, we can actually control the charge on the graphene in order to return the graphene to its direct point, basically turn it to the place where it's charge neutral. We do this by creating a voltage difference between the graphene and a gate, and there's a dielectric in the middle. So this basically creates a capacitor, which allows charges to build up on the graphene. And using a simple DC power source, we can actually control the charge on the graphene at any time. So by changing the amount of voltage and measuring the resistance across the graphene, we can see how much voltage is required to return the graphene to its direct point. And this will tell us whether or not the different biomolecules have actually attached. So you can see all this work here in the sample measurement. We start by taking a control measurement before we've introduced any biomolecules to the graphene. So in our experience, this control measurement never actually starts at 0 gate voltage. And we think this is, that's what the theory predicts. But this is probably a result of some minor impurities that have accumulated on the graphene due to the lengthy fabrication process. But nonetheless, the control serves as a reference point for all the future measurements. So we then add the linker to the sample, and we immediately notice a shift in the direct point in our graph. This lets us know that the linker has successfully bonded. We can see the same type of shifts when we add the probe and subsequently the target DNA. So the measurement of the target is the most important because this is what, if we see a shift here, then we can pretty much assume that the DNA has bonded to the probe and to the graphene. So this picture here on the left shows what one of our current biosensing devices looks like. The gold pads serve as contact points that allow us to measure the resistance across the graphene. And the graphene actually sits in between each of these pairs of contact points. The surface area of the graphene itself is incredibly small. It's actually only 10 micrometers in width. And the clear circle around the center of this of this device is actually a well that we made out of the polymer PEMS. We use this well to administer the different biomolecules. Basically, we just fill them up with the different biomolecules in solution and allow them to sit on top of the graphene so that they can bond. So we then put these chips onto a PCB, which attaches to this breakout box, which is this silver box you see here with the red wire sticking out of it. The breakout box basically just connects to a multimeter and allows us to run our resistance measurements. The gate voltage is applied via this electrode. You can barely see it there. It's the thing hanging from that silver piece. And it actually goes into the liquid and serves as the gate for our gate voltage measurements, with the liquid serving as a dielectric. So unfortunately, our current method of testing devices limits us in several ways. The main problem with this method is that the probability of the molecules actually interacting with the graphene is relatively low. So the graphene has a very small surface area relative to the rest of the chip, which means that there is a very small surface area where they're actually interacting with the biomolecules. So there's this limits the probability that they're actually going to be attaching. Furthermore, there is no pressure being applied to the solution. If there was actually some sort of pressure being forcing the graphene or the biomolecules in contact with the graphene, the probability that they're going to be interacting is much greater. The next problem is that we have to actually wash or fill up the well by hand every time we want to wash it or introduce a new biomolecule, and this is a pretty time-consuming process, and it also introduces the potential for a lot of human error. Another problem is that the setup only allows us to test one device at once using the breakout box, and it also allows us to fill up or use one biomolecule for the whole chip, one target strand of DNA. So this is where microfluidics can greatly improve our biosensing process. Like graphene, microfluidics is relatively new and is receiving considerable attention across many scientific fields. It basically involves the control of different fluids and channels that are only micrometers in width, and it allows scientists to run some pretty interesting experiments that would have been previously impossible. So, for example, our collaborators at the Van Opijnen lab use a droplet microfluidics to isolate single cells of bacteria to independently analyze different materials, or different mutants, sorry. In our lab, we're using microfluidics to help control the flow of the different biomolecules across our graphene devices. So the image here shows what a microfluidic setup might actually look like on one of our devices. You can see how the channel runs right across the graphene, allowing the solutions to actually come in contact with the graphene, limiting the surface area and increasing the pressure at which they're interacting. So my main task this summer was actually to implement these microfluidics onto our biosensing devices. So many microfluidic devices consist of a PEMS mold with the channels ingrained on the bottom. Creating this mold is a relatively simple process that involves first pouring liquid PEMS onto this custom mold with the channels already designed on it. Then you heat up the PDMS until it solidifies, at which point you can remove the silicon mold and introduce the substrate of your choice. At this point, you do a process called O2 plasma etching, which creates a tight seal between the solid PDMS and substrate. In microfluidics, this tight seal is what's most important, because if there's even a little bit of gap between the PDMS and the substrate, the fluid will leak out and it won't go where you want it to, and basically the channel's ruined. So once you have this tight seal, you can introduce the fluid and run your tests. So this picture here is just a quick picture of how the Nano lab runs their setups. The most important takeaway from this is that they can use 2 different pumps to, which are those big red boxes, and they actually use syringes to put the different biomolecules in, and they can actually use this to put different biomolecules in at the same time or at different times with different rates, and it just allows you to, so what this could do for us is it could allow us to greatly automate the process of our biosensing. Instead of having to load and unload the PMS well by hand every time, we could actually just use this to load the different biomolecules and wash solutions in. So this would greatly reduce the time that it takes to measure our devices, and it would also reduce the potential for view and error. So you can also see here that the Nano lab uses, you can see the PDMS mold with the different wires sticking out of it, and they actually attach theirs to a glass slide using this plasma etching. But unfortunately for us, this plasma etching didn't work with our devices. We think it's probably a result of the large surface area covered by the graphene or the gold contact pads that's just sort of preventing the bond from actually forming. So our lab solution to this was the device that you see here on the left. I actually drew this on an AutoCAD program, and we had it made in the machine shop in the basement of Higgins. So it consists basically of a base for holding the PDMS, or for holding, the biosensing device. That's the big square that you see on the bottom. And this has 4 holes in the corner to allow it to screw into a transfer stage that could greatly increase the stability of these tests. And then the lid, the piece that you see on top, is for holding the PDMS with the channels. So the 4 holes that you see around the center of the lid are for the input and output holes for the fluid, and the middle hole is for the electrode, so that we can continue running the gate voltage measurements. The top piece is clamped to the bottom using nuts and bolts threaded through these holes on either side of the base. And the 4 cuts on the top are for putting our gold pins through, so we can reach the contact pads to measure the resistance. So here's what the device actually came out looking like once it was made in the machine shop. You can see we used a clear acrylic lid for the PDMS holder. This basically just allows us to properly align our microfluidic channels with the graphene devices. You'll also notice that there are no cuts for the gold pins. The pins, those cuts actually would make the piece too unstable, and it would probably break if we tried to actually put those in. We're still searching for a solution to this problem, but we decided that it would probably be a good idea just to test to make sure that this device actually works to clamp our PDMS down onto the substrate so that we can create this tight seal. That's so important. The first tests with this device have returned positive results. I was actually able to create a PDMS mold that has our channels that aligns with the lid, and it runs directly across the graphene, and I actually have a video of the device working here. So the important thing to notice is that the liquid actually comes out of the outlet hole. You can see it, it's really hard to see, sorry, but this proves that our device is actually giving us a tight seal and allowing the fluid to run across the graphene. So these results are very exciting and give us hope that microfluidics can greatly improve our biosensing process. So my work this summer is only the tip of the iceberg in the microfluidics and how we hope to implement microfluidics. We will eventually move on to creating devices with up to 20 graphene contacts or devices. And basically what you're looking at here is one of our hypothetical future devices. There's actually graphene in between each cluster of these 4 contacts, and the microfluidic channel wraps all the way around and contacts all of them so we can attach the biomolecules. We're already actually developing a breakout box that will allow us to test each of these pads at once, which would just greatly increase how many devices we're able to test at once and give us a lot more data so we can continue to improve the biosensors. Another option we have is creating multiple different microfluidic channels on our devices. And this would basically allow our doctors to test one sample of a patient's DNA against multiple different target strands or probe strands of DNA. So you could basically test for multiple different bacterial infections on one chip at a time, or simultaneously. So in conclusion, our lab is attempting to create biosensing devices that can selectively detect different biomolecules and revolutionized the way that doctors diagnose patients. We use graphene in these devices because its unique band structure and Dirac point make it incredibly sensitive to any charges on the surface of the graphene. And my research this summer was focused on developing microfluidic devices that would allow us to increase the sensitivity and consistency of our devices. By the end of the summer, I was able to actually successfully run microfluidics across the channel, hopefully opening up a number of new possibilities. So I'd just like to really quickly thank the people who helped me out this summer. From the Birch Lab, Kenneth Birch for allowing me this amazing opportunity to do research, and Narendra Kumar and Mason Gray for helping with the day-to-day struggles of lab life. I'd also like to thank our collaborators at the Opine Lab, specifically Tim Van Opine and Juanse Ortiz Marquez, Thomas Pekka, and Derek DeVault. I'd also like to thank Stephen Shepard from the BC Clean Room and Paul D from the BC Machine Shop. So, do you guys have any questions?
Questions?
Was that just, in the video, was that just water you were flowing?
Yeah, it was just water.
Okay. And in the future, what?
I mean, it'd be our solutions with all of the biomolecules, or even like the washing solutions that we use to clean out the device once we've had them.
Gotcha.
Yeah.
So when you use those, you can then just like put the cleaning fluids through them and just like wash it out. And are they reusable? Like, can you just?
We're working on that. We're not entirely convinced that they're completely reusable. We have to think of a way to get rid of the different attached molecules.
Yeah.
Acetone might work, but I'm not sure what that would do to the graphene.
Gotcha.
Yeah.
Can you go back to the diagram of like the capacitor with the dielectric and
Yeah. Let's see if we can do this.
so what material is the gate?
The gate's the electrode. We've been using, we have used a combination of a silver chloride electrode and also a platinum electrode. The problem with the silver chloride electrode was that it was leaving, was like depositing some sort of, we think, solid chlorine onto the pads and like just basically contaminating the devices. And then we switched to a platinum electrode in a PDS solution.